Hello folks, this is Sridhar Ramakrishnan and welcome to our webinar this month. Before we get started, a few bookkeeping items just to alert everyone. The presentation will begin shortly with Harris starting about in a minute from now and going on until approximately 1 o'clock. He's agreed actually to stay on for a few minutes after that in the event that there are additional discussions and questions, etc. The slides and the recording will actually be available at the end of the presentation. Just log into your Malibo account and you should be able to view the slides and the recording at YouTube. Please keep your telephone or microphone muted at all times unless you need to ask a question. And if you actually dialed in using the telephone, please make sure that you entered your audio pin when you dialed in. Otherwise, there's no way for me as an organizer to unmute you. If you've actually called in using VoIP, there's no problem. I should be able to unmute you shortly. But just to prevent all the ambient noise of cell phones and clicking on the keyboards, please keep your microphones or telephones muted, please. Thank you. Let's see. Please ask questions. Please make the session as interactive as possible. And Harris will actually keep time, and in the event that your question is better deferred to the end, he will ask that you hold your thought until then. If you actually prefer to ask your questions by chat, please write them in the little chat window on your screens, and I will relay them to Harris. I guess with that, let's go ahead and get started. We're delighted today to have Charalampos Harris Chelmis, a PhD candidate at the University of Southern California in the Computer Science Department, to talk with us about predicting communication intention in social networks. As I mentioned, Harris is a PhD candidate working with Professor Victor Prasanna in the Department of Electrical Engineering at USC. His research interests focus on modeling complex networks, their properties, hidden structures, and dimensional interdependencies, mining large-scale, real-world social networks, and designing efficient, scalable algorithms by combining graph theory and semantic web technologies, big data analytics, machine learning, sociometric features and measures. His research has been published at several top venues, including Socialcom, ASSONAM, TOIS, and SMAM. He's received his Master's of Science in Computer Science from the University of Southern California in 2010, and his Bachelor's in Computer Engineering and Informatics at the University of Patras in Greece in 2007. With that, let me turn it over to Harris. Take it away.
Thanks, Sridhar. Hello, everyone. I would like to thank my advisor, Professor Prasanna, and our previous postdoc, Vikram Sarathia, whom I have been working with to produce this research. I would like to start by saying that networks are everywhere. Particularly social networks have emerged starting from anywhere in between computer communication networks, phone networks, email communication. Recently we have seen that NSA in the US has been studying logs from phone communications to mine interesting facts about users. We also have movie networks such as IMDb, where we have connection between different movies, actors participating in those, starring in those movies, directors, and movie attributes. We have affiliation and co-authorship networks such as the DBLP, where if we analyze these networks, we can find relationships between researchers. Our researchers collaborate to come up with new ideas and then keep track of what conferences topics have been over time. We have professional networks such as LinkedIn or Malibo for what matters, where people connect to find jobs. We have friendship networks such as Facebook or Google Plus lately. We have information networks such as Twitter, where people tweet interesting facts that others would like to know. And then we have formal networks such as organizational charts, where are imposed as a structure by a formal organization. And we have inferred networks of interactions between people in, say, question and answering websites as a Quora. Finally, we have other kind of interesting networks such as couchsurfing that has recently been studied to better understand social phenomena that evolve around the globe. Of course, we have more complex networks than each and every individual networks that I have described. Such is, for example, the communication network from HP Labs, where you have the formal organizational structure being shown in solid black lines, and then you have the actual email communication between different users. And the idea is to try to capture as much of the rich, complex structure in these networks and try to understand how different aspects of these networks interact. What are the interplays and interdependencies between these networks. Because of the richness and number of social networks out there, social networking analysis have emerged as a powerful domain and technique to analyze them in multiple applications and in numerous contexts. So, for instance, you have businesses that use SMA to analyze and improve communication flow in their organization or with their networks of partners and customers. You have law enforcement agencies using social networking analysis to identify criminal and terrorist networks from traces of communication that they collect, and of course identify key players in these networks. You have social networking sites like Facebook that they are trying to identify and recommend potential friends based on friends of friends relationships. Or civil society organizations that are trying to uncover conflicts of interest in hidden connections between government bodies, lobbies, and businesses. Online social networks in particular are interesting due to the fact that their users interact with one another and content that they create and consume. This in turn produces rich interactions that enable more complex analysis than mere social networking analysis. So we have anything in between friendship based on similarity. Similarity is a very difficult thing to define, up to following relationships based on interests, and interest is also vague. However, the problem with online social networks is that they are very, very noisy due to the vast heterogeneity of their users and their target audiences and applications.
Harris, can I just interrupt for 1 second?
Yes.
There is quite a bit of ambient noise, so just a reminder for all those who joined late: if you dialed in or you're on micro, or you are communicating through VoIP, please keep your microphone or your telephone muted. Otherwise, there is quite a bit of background noise that we're hearing. If you dialed in and you haven't entered your audio pin, you won't be able to ask questions. So please, in that case, send me the questions via chat, and I will relay them to Harris, or else enter your audio pin, or else use VoIP for the audio portion of this webinar. Thanks. Sorry, Harris.
Sure, no problem. So let's see. So contrary to online social networks, collaborative technologies have penetrated the enterprise world as well. And even though enterprises still heavily rely on email traffic to exchange information between co-workers, there have been multiple informal collaboration platforms that have been adopted over the years. I have a few examples here, ranging from pure Microsoft products like SharePoint to web-based products such as Google Documents, and then Twitter clients for the enterprise such as Yammer, for instance. And the adoption of these collaboration technologies have enabled the existence of multiple communication channels, informal communication channels, that really speed up the share of timely and relevant information, and have made the search for data and experts easier. but that's in the context of enterprise. Of course, because the enterprise focus is on business perspective, collaboration solutions at the workplace also focus on day-to-day problems, and therefore offer a less noisy environment than online social networks, with focus on problem solving, question answering, and information seeking kind of discussions. Informal collaboration media improve collaboration and information exposure by assisting in breaking barriers in the formal organizational hierarchy. So instead of relying on this formal stringent structure to find somebody who knows something, if you don't know that someone, that subject, without the informal collaboration solutions, you should have to ask your manager or your teammates, and then if these guys would be able to suggest somebody, then you would actually find the person of interest. But using collaboration techniques, you can span these barriers and perform efficient and effective team building, and of course propagate knowledge across the enterprise so that you can have a body of knowledge that is being shared among your colleagues in an enterprise. So, of course, there are a few opportunities that are being magnified in an enterprise environment, such as expert identification, where in this case we are interested in identifying true experts versus influencers, who are important people in the structure of the network, important in the sense that they are crucial for information flow. We can apply different techniques to identify how indeed information flows in this kind of networks, and if it follows the organizational chart, or if informal interactions take over. And then identify trends such as what is the company focus, or what it should be if their customers are feeling like the company is falling behind, and so on. Finally, we have opportunities for mining collective knowledge, in a sense integrating atomic knowledge to get the global knowledge in an enterprise, and then translate this knowledge in a sort of management and maintenance system, so that we can propose new solutions to problems as they come by and identify best practices. These are all aspects that I have been exploring in my PhD thesis work. Today I will be only focusing on predicting communication intention, and this is an important problem because, as I will show, we can use the understanding of this process to recommend the experts when someone has a problem at the workplace, and direct them to the correct expert to solve a question or problem they might have. Of course, collaboration at the workplace is not just a heaven that we can dive in and mine out solutions. There are a few difficulties. We still have informal interactions. The data that we are dealing with are unstructured and heterogeneous. And then there is the important question of how to formally model knowledge. And I have an example here where you have an informal discussion. Somebody jumps in a kind of discussion and asks a question about where to find a Java source code, for example. Then there is this expert user, supposed to be an expert as identified by the system by previous posts, that supplies an external source, external in the meaning of the network that these users are discussing. So this is not the exact solution that we are seeking. And then a reply comes back and says, okay, I have seen the solution, but it's not exactly what I am currently looking for. So a solution might be given, it might not be exact, and it might not be good enough. So we want to solve these kind of problems as well. So to be able to attack these kind of questions, people have tried to model networked data in order to either perform some predictive social network analysis, or some descriptive social network analysis. And I will be focusing on the predictive aspect, where we are trying to predict communication intention. In that sense, networks can be represented as graphs and have been represented as graphs, where nodes have been traditionally the users in a social network, and edges between such nodes, users, have different meanings depending on the semantics that we impose on these edges. And I have indicated some examples here, so it could be friend-of relationships, it could be interaction relationships such as how many times you have called somebody or you have sent an email to somebody. It could be information flow in a fashion similar to Twitter where somebody retweets a tweet and so on. Of course, we can have a weight in the edges that differentiate various edges between people, say for example in terms of communication frequency or the distance that people have in the network, if they reciprocate a relationship or not, and based on the type of interaction. Of course, we can have a combination of those. However, traditional social networking analysis techniques only distinguish between pairs of people that are linked versus those that are not. And of course, user interactions in social media are much richer than that. That we have heterogeneity in both the objects and the link types. Both nodes and edges may carry attributes, which in turn might be connected. And for example, I have stated here that there's a correlation between the attribute values and the link structure, which has been traditionally exploited by previous work to perform link prediction in friendship networks. Or there might be a correlation among the attributes of related nodes. This kind of technique has been used in collaborative filtering so that we can recommend products to consumers, for example, by examining the purchases of other consumers with similar purchase behavior, for example, in Amazon. Then there are node dependencies. Users tend to form groups or communities based on their common interests, topics, or by their location, for instance. And then we have partial observation in a sense that we might have a network of people. We might have knowledge for some of them with respect to who they vote, if they are liberal or Democrats and so on, but not everybody, and in that case we want to infer some sort of information. Then we have the big data problem, where we have billions of users, billions of connections, and billions of documents, different kinds of documents you can think of as multimedia or text and so on. And then connections, as I said, are rich and multiple. Some unique characteristics of network data that I would like to point here are temporality, context, and multimodality. In a sense, temporality means that affiliation, interests, and friendships change over time, and we would like to keep track of that and examine that and exploit that in our applications. Context means that we have information varying based on spatial, temporal, or topical aspects. Relationships keep changing if we go from one place to another, or if somebody joins a different company than they have been working recently. Time is important because you can have multiple connections with multiple people, but connections change over time. For example, if you are calling somebody, you might be connected, but after a minute or so, you might be disconnected in the network and so on. Context multimodality I'm referring to the fact that we have different content media such as text, videos, photos, and so on. In that sense, edges are more than limbs, and we should be aware of this fact. There are edges of multiple types. There are edges that carry trust or sentiment between people, or between people and products for the sentiment matter. We have strength, which we can define in multiple ways. There's a timestamp associated with an edge, and then there are a number of multiple connections, if you wish, that two people or a person and the product might have over time and over context. So in that sense, edges reveal something about the relationships between nodes, and we should somehow mind this fact when we use edges in our analysis. In the figure that I'm providing here, I'm trying to capture the different contexts that people interact at the workplace. As an example, you have an employee that works on a specific project and asks a question in some collaborative media at the workplace. There is another employee that follows the specific thread but does nothing other than that. There's an employee that replies directly to the question, but instead of providing a sufficient answer, refers the first user to another employee and a solution that has been posted in a different media altogether. So to capture this kind of behavior in complex social media at the workplace in particular, we have come up with a comprehensive context model in which we define various dimensions of informal communication at the workplace, while at the same time providing flexibility for adding new context in the future. And of course, for the sake of time, I will not go into the details of this model. You can take a look at the papers that I have presented already. But I would just like to mention that this model facilitates advanced analysis of collaboration data, and is one of the applications of which is the problem that I'm describing today. So in general, to capture these rich interactions in social media, we have come up with a model that instead of relying to the social network, the graph that represents users and their connection, we enrich it with other information as well. Even in the single social layer, we have edges that are multiple. We have multiple edges between two users, depending on time and context, and then each edge also carries a timestamp. Then each user is connected to the content that they have shared in the internet, in the social network, or somehow have contributed to it or interacted with it in any sense. So for instance, if somebody likes a photograph, or if they have commented on a micropost issued by another user, then they are connected to this content as well. But still, we don't stop there. We annotate the published content with whatever information we can. And with whatever information we can, I'm referring to three different aspects that we have considered: the what, the when, and the where dimensions of content, based on which we analyze the content with respect to the representation of text in bag of words, which is very simplistic, identify the entities, hashtags that are provided by users and are usually more meaningful and used for organizational purposes, latent topics that describe the content of the actual message or document, if you wish, that have been used. And we also store a timestamp and allocation information if we are given such data. Further, we link these annotations, if you wish, to external repositories, ontologies and folksonomies that are available in the internet, so that we can get a better understanding, better semantic meaning of what we have in our repository. And of course, based on this model, we have created social algebraic operations that enable complex mining and analysis and correlation of different domains, both across time and across contexts. So particularly for our problem, you can think of it this way. We have a communication graph which we are given as an input, and then users are represented by a node, and then connections between users are directed because they indicate communication initiated by someone. And then you have a connection if at least one message has been sent from one user to the other. And then reciprocity in this case is defined as follows. You have user U that has sent a message to user V, and then user V has sent a message back. So for our problem, we are given this input, and we want to identify for a single user at a time what are the possible other users that this user U is going to send a message in the future that these other users have not been contacted by you before. So you can jump in and say, okay, I know this problem. This is link prediction.
Eris?
Yes.
I have a quick question.
Yes.
You know, if you just go back, on this graph, are there annotations on the edges, you know, per your previous slide?
Yes, so I'm going to talk about this in a minute. If you just focus on this graph, it's just a communication graph, right? So no annotation whatsoever here. So you can think of it as a typical link prediction problem, but then you should consider these aspects. So the edge semantics are different in this case because we are having a conversation, communication between users rather than friendship, and I will show you in a couple of slides why this is important. There's also contextual and temporal properties that you should consider. So in the edges that I showed you earlier, I kind of hide the semantics. So if you have an edge between users 1 and 2 sent in a specific topic, if you wish, J1, or a group J1, this is different than sending a message between the same users but in a different topic or a different group altogether. And we should distinguish between these two, because if we recommend user 1 to send a question to user 2 about sports and user 2 has no idea about sports, then they will get rubbish back as a reply. Also, directionality matters, because if user 1 sends a message to U2 and we were to predict that U2 sends a message to U1, then we would be wrong. In essence, what our problem boils down to is are these two questions. We want to understand what makes people initiate conversation with strangers, and in fact try to understand who individuals choose to collaborate with and for what reason. So in previous work, people have used homophily to relate, to better understand and capture the process of people linking to others with similar characteristics. This has been a fundamental concept underlying social theories, and it's the basis for link prediction, based on which similar nodes tend to cluster together, connect together with other similars. So I would like you to think how this would help us solve our problem in this particular case. And during that thought process, I would also like to point out that there have been multiple prior works that compute similarity or homophily based on multiple approaches. I have included some here, such as machine learning approaches, approaches based on the node attributes, because I have already mentioned that there is a correlation between similar nodes with similar attributes and an edge between those nodes. And then there have been many works that have been relying on network structure to identify possible new links between users. However, think of the transitivity property in a network. So suppose that you have this communication network where node X has sent a question to node Y, and then node Y has sent a question to node Z. Then does that infer that X is going to send a message to node Z as well? Because that's one traditional way of thinking link prediction in a friendship network. You could consider this approach here as well, but intuitively it doesn't work like that. And for instance, if you further go one step further and include context, then if X asks a question or send a message to node Y about, say, football, and then Y send a message to node Z about politics, then should you infer that X is going to contact Z? And if then in which topic? Is it going to be football? Is it going to be politics? Or is it going to be something completely different? So in that sense, transitivity doesn't work in our case as well as in, say, friendship networks. So going back to our problem, we start with constructing a communication network from threaded discussions in an informal collaborative platform at the workplace. So you have this traditional thread structure where user A writes something and then users reply back, which we can convert into a bipartite graph and then further reduce it into a post-reply network, which ultimately becomes our communication network. But we don't stop there. We take this network, which, as I have already said, you have multiple edges here because you send multiple messages to multiple users, and then augment it with the actual content of the posts, which are annotated by different attributes that I have already described. The content is a bag of word representation. We have hashtags and we have we have timestamps for the post as well. And in this particular case, we were also provided with information about if the specific post was sent or shared in a group, in a particular group of users, or it was fed in the corporate-wide feed. For groups and hashtags, we use WordNet to further annotate them with synonyms, hypernyms, and hypernyms. And by synonyms, I mean expand terms with others that denote the same concept, such as, for example, car and automobile. For hypernyms, I'm referring to concepts of more general meaning than a word. So, for instance, furniture is a hypernym of bed. And then hypernyms are more specific concepts, such as bed is a hypernym of furniture, and so on. So in that sense, we have a representation of users based on their connections and their content. And the content is split down into features of multiple types, both textuals and temporal. And then there comes the question of how to kind of calculate similarity between different users. And for that, we have to calculate similarity for each and every feature in our model. So to calculate similarity for textual concepts, we have used Jacquard index, which has been shown to provide a good trade-off between simplicity and performance. And if you give it two sets, then you calculate the intersection of the two sets and then divide by the union of those two sets. So if you can think of two terms, two hashtags for instance, we calculate the Jacquard index for the two terms using the set of their synonyms, their hypernyms, and their hyponyms, so that we have three different measures, synonym-based, hypernym-based, and hyponym-based, and then we calculate the semantic similarity between the two terms using the weighted sum of these three similarities. Of course, there's a caveat here that you might have concepts belonging to the same subtree, in which case the similarity of their synonyms, hypernyms, and hyponyms will be 0. So we looked at three kind of structures and then combine the different sets so that we can calculate the similarity of their combined sets as well, and also consider the syntactic similarity between different terms using Levenshteinian distance. A better maybe technique would be to calculate the distance between two terms instead of relying that, on the fact that they will be in the same tree. So maybe a path-based metric would be more appropriate to use, and we will explore this in the future. For the bag-of-word kind of features, we use a traditional TF-IDF weight vector representation, and they use the cosine similarity to calculate similarity between bag-of-words. For date similarity, we are using this formula where if two dates are too far apart, too far is defined by a threshold TD, in our modeling is 365 days, so if they are 1 year apart or more, then the similarity is 0. Otherwise, the similarity is 1 minus the difference normalized by this threshold. And then there's a similar formula for time similarity where TT is now defined as a threshold of 1 day. The similarity is measured in seconds, and then the timestamp similarity is the weighted average of these two. However, if you think of computing similarity between two hashtags, for instance, then you can say, oh, but if you have a post that has multiple hashtags, then how do you calculate similarity between these two posts, these two microblogs? And then in order to account for this peculiarity, we wanted to calculate set similarity. And for that, we use a variation of the hashed-off point set distance, based on which we average the maximum similarity of features in set A with respect to features in set B. So think of A as a set of hashtags for a microblog, think of B as a set of hashtags for another microblog, and then we take the similarity between each and every hashtag in set A and compare it to hashtags in set B, take the maximum similarity and average overall elements in A. Of course, this measure is asymmetric with respect to sets, so the set similarity between A and B is different than the set similarity between B and A. And this, I claim, is a good thing, because we want to have the asymmetric similarity calculated for different users because of the directionality problems that I discussed earlier. So finally, the user similarity boils down to this simple formula, if you wish, where we weight the content similarity and the network proximity between two users, and weight the average using a trade-off parameter lambda. Again, this is asymmetric with respect to users. The content proximity is calculated over all user microblogs, which microblog similarity is calculated over the different features, as I explained earlier. And the network proximity, for simplicity, is calculated as a variation of the common neighbors similarity where you have the neighbors of user U and the neighbors of user V, take an intersection and then normalize by the number of neighbors of user U, so that we can make this asymmetric as well. So finally, the algorithm for solving our problem becomes this. We construct the augmented communication graph first, and then based on this graph, on the fly, given user U, we compute similarity with other users that U has not initiated the communication contact before. For all facets of the previous communication, in a kind of top to bottom tree similarity calculation. To evaluate our work, we have used the complete snapshot of the corporate microblogging service, which resembles Twitter and was used by a Fortune 500 company. The dataset contains of about 4,000 unique users that have exchanged about more than 16,000 messages in total. These messages are split in about 8,000 threads. We have 18 discussion groups, and then the number of hashtags is kind of low. It's just 637 unique hashtags. So based on this data set, we've inferred the directed communication graph and annotated with the content. And content is annotated using WordNet to get the semantic similarity for hashtags and groups. For our evaluation, we have focused on the largest connected component of this dataset because it was sparse. So the largest connected component consists of 582 users. The edges between the users, unique edges between users are about 4,000, and these users have exchanged about 11,000 messages. In our analysis, we have shown that this network, both the initial dataset and the largest connected component, exhibits small world and scale-free network properties. And that is good because it suggests that we can use the same kind of approach in other networks as well that show the same properties, such as online social media. Scalability, of course, will be something that we'll have to address, but that's a different question here. And then I would like to show the just one analysis that we have performed, where we compare the number of people that users have sent a message to and the number of replies they have gotten back by these people. And there's a significant correlation between the two numbers, which suggests that there's a tendency of users to reply back when they receive a message from others, which, however, is not true, because if we measure the number of reciprocal links, and it turns out that it's only about 20% in our data set, whereas in the largest connected component, the same reciprocity link percentage is about 23%, which is not that bad, but not that good either. So for our evaluation, we have taken the data set and performed a four-fold cross-validation, where we randomly sample 100 users and recommend the top K links for each user, and measure accuracy in terms of precision in these top K links that we recommend, recall for the top K links, and then mean reciprocal rank. And we experimented with K equal to 1, 5, 10, 20, and 50. Now, keep in mind that in the largest connected component, the average degree of each of nodes is 12. So anything above 10 will kind of degrade our results, just because we cannot recommend more users than the actual links are there. And then we compare our approach to 4 different baselines. The first one is random selection, of course, which is the trivial thing to do. The second one is shared vocabulary, according to which we measure the cosine similarity between the hashtag vectors of 2 users and then recommend those that are quite similar. We use a shortest distance measure based on which we try to capture the transitivity if such a thing existed in the communication network we are examining, and of course the number of common neighbors, with the intuition being that if you share multiple, if you have frequent communication with some people, then and those people have frequent communication with others, then what is the probability of having communication with those others yourself as well? The intuition behind using shared vocabulary is that we measured vocabulary alignment in this dataset between users, and we found that there is a significant overlap between users that are in close in the network. One distance of 1 means that they are indeed connected, and then there are 2 hops, 3 hops, 4 hops, and so on away in the network. Interestingly, we found out that similarity is quite high, up to a distance of 6, which is not that obvious in online social networks. This drops in about 3 hops away. And this explains in essence why the shared vocabulary doesn't work, as I'll show you in the next couple of slides. So here is a table that shows the performance of our method compared to the baselines for different values of k. This is for precision, this is for recall and MRR. And down here I am presenting the percentage improvement achieved over the best performing baseline, which is indicated by dark bold numbers, if you will. So we can claim glory and say, okay, this works better than the baselines. In both cases, we get good results with respect to the baselines, but then if you look closely at the numbers, you can see that precision, recall, and mean reciprocal rank is still low, even though it's better than the baseline. So we wanted to dig deeper and see why this is happening. One clue is that this is just a uniform model that we have used, based on which all weights are uniform, so they are equal, and the lambda parameter that controls the trade-off is set to 0.8. So there are other models to consider, and for that we have applied a grid search over ranges of values for these parameters. Here are a few examples that I am using in the plots that follow. So we have the initial uniform weighting scheme. We have a scheme that focuses on tags, a scheme that relies only on group information, a scheme that relies on word representation, different time schemes, and then different mix schemes. And this is what we get as a function of parameter lambda. Baselines are down here in both cases, and all of our schemes are up here. So in all cases, we are performing better than the baselines, and the more we weight on the content similarity, the better the approach seems to work. We get better results here, as you see, overall. Yes?
There's a question that has come in. The question is, do you think these results will be reflected in another large-scale enterprise network?
Yes, I think so. And I have another plot here that suggests that the more evidence you have for particular users, then the better the accuracy becomes. It tends to go up to 1, but we are overall hurt by people that do not have enough neighbors or enough posts to share for us to mine and get a better understanding of their behavior so that we can propose links in the future. This is something else that I wanted to show, which suggests that different models, different weighting schemes work better or worse for different users, and that suggests that personalization is needed to achieve a better overall accuracy. So in a sense, these numbers are not indicative of the true potential of this method. We should look at particular users and select a better model for each and every user to get better and better results that go up to accuracy of 1. Another example that suggests that the more evidence we have, the better, is that is shown here, where we restrict the users we predict links for based on those who have enough statistical evidence to share, and you can see that the mean reciprocal ranks becomes very significant in this case, and tends to increase the more we pay attention to the content instead of the connections in the communication graph. So, of course, as I said, there are open problems such as scalability issues. One question is if this is going to work in a huge network or not. And then we would like to also replicate the results for online social media if that's possible, even though we have suggested that online social media are way noisy and way less focused than collaboration platforms at the workplace. Another thing is the personalization of the weighting schemes, so that we can learn different weights for different users, and then we should also try to learn weights on the fly. In the potential application sections, this approach could enable contextual expert recommendation for question and answering, or search for interesting people to collaborate. And for that matter, for the contextual expert recommendation, we have actually built a system which we are actively trying to get performance evaluation with real people in the enterprise we're working with. And the system works as follows. So you have an employee ID so that you can have the history of that employee, and then the employee composes a message, and then as the message content unfolds, the system suggests possible users that might be interested in this topic, or possible users that are able to answer this topic with some confidence level. Our system also supports semantic social network analysis for the enterprise based on our model, the context that I showed earlier. We have implemented this model, the multi-layer model, in an ontology framework that enables us to issue semantic queries and get interesting results that vary from the atomic level to the microscopic level that goes up to the complete corporation, and get a better understanding of what people are talking about altogether. So this is everything that I wanted to share with you today. Thank you very much, and if you have any questions, let's open the floor for a discussion.
So I guess while people are thinking of questions to ask, I guess, Harris, let me start. I guess, the algorithms that you discussed, you've actually implemented them, correct?
Yes.
And so can you speak a little bit, I guess, in terms of efficiency and the issues, surrounding implementation, because I think they pertain directly to the question on scalability, I believe.
Yeah, so the focus of this work was not that much on scalability, but I have implemented this in Java, using object-oriented programming, and they work fine. I mean, for the data set that we have, for the largest connected component of the 592 users, for a particular user to get a reply back, it takes less than a second. And if you consider the similarity metric which I described here, then because of the asymmetric aspect, you can compute this similarity for different user pairs in parallel. And as new content comes as the time unfolds, then the similarity might change, but it only changes if you have a better element to include in this maximum calculation for the hash-default points and distance. So there are definitely some optimizations that can be performed, which we haven't touched yet, but the implementation suggests that it works pretty well as is.
I guess what issues do you see if you know, an actual service like Twitter or Facebook or LinkedIn were to try to you know, adopt some of your approaches?
Can you repeat that?
What issues do you see? You know, I guess you know, apart from sort of you know, resources of machines and so on, what issues do you see if you were to try to extend this, you know, not from beyond 4,000 users to something like, you know, 100 million users? I mean, you know, I know you've not explored scalability, but can you at least speak to, you know, the issues that you see potentially coming up?
So for scalability, you have to compute the point-wise similarity between all potential users that you can think of, but this is a generic problem that every algorithm has out there. Anyhow, if you want to suggest links to people that are not corrected anyway. Another problem that I can think of, and I would like to touch, is what happens with noise, because I said that the enterprise network is really focused. So perhaps the communications, the messages that people exchange are more related to work practices than, say, personal matters, sports, politics, whatever. And it would be interesting to see how the framework would behave in an environment like Twitter, where you have all sorts of posts that are not as focused as in the enterprise.
Okay. Thanks. Folks, we have reached 1 o'clock. Any further questions for Harris?
I had one question. Hello?
Go ahead.
Okay. So it seems like message consumption information is available in this data set. Is that correct?
Message consumption, meaning what?
So this is, it's not like an email system where you see everyone who receives a message, but
Yeah.
people can actually go and search for information that they're looking for. So it seems like that would be very useful information. Is that something that's available in the system or not?
So what we currently have is this threaded discussion. This is our data set. But yeah, you can think of the system as a clone of Twitter. So people send a tweet, say this is the initial tweet, and then people reply back or retweet, or think of it as this way. But then, as in Twitter, you can search for particular hashtags, groups, or messages anywhere. So you have a corporate-wide feed that all messages have been sent to, and then you can search through over all these messages, which leads to information overload if you think about it. So yeah, message suggestion would work as well.
Any other questions for Harris? So I guess if there are no further questions, I guess continuing our past practice, let's give Harris a warm round of applause with a virtual clap. You can all unmute yourselves here. So Harris, that's our convention here, since all of us are remote. Thank you very much for an informative presentation. The slides have actually already been uploaded to the site. I will actually be recording this section has been recorded and will be on YouTube shortly in a couple of hours. Just want to remind everybody that our upcoming seminar series has been posted to the site, so you can actually see what's upcoming. Our next seminar is on June 21, when Dr. Frederick Sheldon from Oak Ridge National Labs will talk about failure impact analysis using cybernomic analytics. So join us then. Thank you very much, and thanks again, Harris.
Thank you all for attending.